Good day, students. So in the last video, we have seen about characteristic impedance, impedance matching, okay, decibels, and signal to noise ratio. And also about S parameters. Fine. So in this video, we will be discussing about average value, RMS value, and rest factor. Along with this, we'll also have a go through about sensitivity, selectivity, and dynamic range. Okay, with that, our basic parameters will be over about RF, and then second half we will move on. So, what is first of all average value? So in RF systems, the average value refers to the average power. Okay, average value if we take itself, average power should come into the scene. So average power, which is the total energy transferred over a period, typically including both the signal burst and the time interval between pulses. Before the starting of the signal and also the time interval between the pulses. So that is our average value. So the average value of a signal is usually over a time period. Fine. So our definition for average power or peak power will be given by average value is equal to average area under one cycle divided by period. Okay. So coming to a peak power, it represents the instantaneous maximum power, while the average power is the time average power over a longer period, encompassing both the signal and the time between the pulses. So our whenever we take average value into consideration, we always take the peak power and the instantaneous maximum power, average power, peak power and average power. So the peak power is the instantaneous maximum power, and the average power is the time average power over a longer period. So the time interval between signal burst and the time between the pulses. So let us see the importance of average value or average power in RF systems. So first, when we see it is compliance, okay. So many regulations specify maximum average power limits for RF devices, ensuring that they don't cause interference or exceed permissible emissions. Okay. So compliance means, see, for our certain systems or components, they will have a particular range to which the power should operate. Okay. So more than that, if it goes, okay, what will happen? It will cause some distortion or the damage to the elements, damage to the components. So it should compliance. Compliance means with the standards, go with the standards. So that is about compliance and component design. So our average power plays a role in component design. Component design is just amplifiers and power dividers. So we know very well about amplifiers and power dividers are often based on average power ratings, as they need to handle the average energy transfer over time. Okay, so we have power ratings even for our air conditioners, fridges, etc. Right? So similarly, for your RF component designs also, they have power ratings. So within that, it should operate. More than that, if it goes, there will be damage to the components. Then system performance. Okay. Average power can be a key indicator of overall system efficiency and performance. So the calculation for average power will be average power is equal to total energy divided by time period. Okay, that is the signal burst, starting of the signal burst and the time interval between pulses. Okay, the time includes both the pulse duration and the time between pulses, as I said earlier. So the average value, okay, can be given for a pure sinusoidal voltage as V average is equal to 2 divided by pi V peak, and which will be almost also equal to 0.637 V peak. Okay. So that is your so that is your technical definition for technical expression for your average power. That is V average is equal to 2 divided by pi into V peak, which is equal to 0.637 into V peak. So in RF, this average power, okay, is less commonly used for AC waveforms, okay, but it is used for rectified signals, and also used in power calculations, such as average power over time. So next is coming to RMS value of the AC. So we finished about average value or average power, then RMS value. So RMS value is the square root of the average of the square of the instantaneous values. Square root of the all currents over one cycle. So RMS will be given as root of area of one cycle of squared wave divided by base length of one cycle. This is your formula for RMS current. Okay. And you even have a expression for RMS voltage, which is VRMS. VRMS is equal to VM divided by root 2, which is equal to 1 by root 2 will give you 0.707 into VM. And also for IRMS, if you solve this square root expression, we'll be getting as IM divided by root 2, which is equal to 0.707 IM. So these two are the expressions for your RMS value. Root means square value of your system. So in an RF system, the RMS value is a crucial measurement. It represents the effective magnitude of a varying signal. So a signal parameter called magnitude can be represented using your RMS value. So mainly our RMS value is used in spectrum analyzers and in power meters. Okay, there and all we use RMS values. Spectrum analyzers, you would have seen in your laboratory, spectrum analyzers, and also in power meters. Power meters in your first year lab, you would have seen power meters. Fine. So for a sinusoidal RF signal, the RMS value is approximately 70.7% of the peak value. Should be a known information. Clear? Next is our crest factor. So crest factor is an important concept in signal processing that compares the peak amplitude of a waveform relative to its average value. Okay, so what is crest factor? Is the ratio of the peak value to the RMS value. Okay, peak value to the RMS value of a waveform. So how do we express crest factor as? Is the ratio between the peak amplitude of the signal and its root mean square value. And it's expressed in decibels and is calculated using the following formula. The general formula for crest factor would be V peak divided by VRMS. Okay, in logarithm term, we see as 20 log of peak by RMS. That is V peak by VRMS. So where peak is the maximum value of the signal and RMS is the root mean square value. Clear? So a higher crest factor. So our crest factor should be high or low. So a higher crest factor leads to intermodulation distortion. So it will degrade the signal quality. But if the low crest factor is low, signal is distorted by noise and interference. Okay. So, and it is important in RF amplifier design. High crest factor signals may require amplifiers with larger dynamic range. Okay, so it should not be either large or low, your crest factor. Okay, crest factor, if it is present in the signal itself, it will cause degradation of the signal quality. So it is important to remember the expressions for your average value or average power, then RMS value and crest factor, which will be useful for your problems also. Next, let us move on to sensitivity, selectivity, and dynamic range. Sensitivity in RF systems. Okay. So sensitivity, it refers to the minimum input signal level that a receiver can detect with acceptable performance. Okay. It is the minimum input signal level that a receiver can detect. Okay, the device should perform well also, but it is the minimum input signal level. Okay, it is usually defined in terms of bit error rate, signal to noise ratio, or output signal quality. So we have a small derivation on how we arrive at sensitivity. Okay, so RF, it is expressed in dBm. So decibels relative to 1 milliwatt. Okay, your RF sensitivity is represented in dBm, decibel to 1 milliwatt, relative to 1 milliwatt. So your formula for sensitivity could be given by, it is derived from the input signal power and the received signal power. So sensitivity is given by minus 174 plus 10 log B plus NF in dB plus SNR min. So what is minus 174? It is the thermal noise floor in dBm per hertz at room temperature 290 Kelvin. Okay, it is the thermal noise floor. Then B is bandwidth. B is bandwidth in hertz, and your SNR min is the minimum signal to noise ratio required for acceptable performance. Okay, require for acceptable performance. And your NF is the receiver noise figure in dB. So your sensitivity is a combination of all the bandwidth, noise figure, and signal to noise ratio. All three are related in your sensitivity. So if we solve this minus 174 dBm plus NF plus 10 log B plus SNR min, you get your sensitivity of the signal. Clear? Next, dynamic range. So for sensitivity, you need to know what is sensitivity and the expression for sensitivity. Then dynamic range. So dynamic range is the difference in decibels dB between the minimum detectable signal. Minimum detectable signal is the lowest signal. Okay. Minimum detectable signal is the lowest signal set by the system's sensitivity or noise floor. Okay. System sensitivity. So here sensitivity comes into the same. So it is the difference in decibels between the minimum detectable signal. Okay, the minimum detectable signal and the maximum usable signal. Minimum detectable signal and maximum usable signal. So dynamic range could be given like this. Maximum input signal that circuit can tolerate divided by minimum input signal level with minimum SNR. We can also express this dynamic range as P max minus P min in dB. So where P minimum is the smallest signal the system can detect linked to sensitivity, and P max is the largest signal the system can handle without distortion. Okay, you have various types of dynamic range. There are two types, linear dynamic range and spurious free dynamic range. So what is linear dynamic range? Linear dynamic range, it's the measurement of the minimum detectable signal to the maximum signal that will start to compress the receiver. So it is the measurement of the minimum detectable signal. What signal can be detected minimum? Okay, so that is relating to sensitivity and to the maximum signal that will start to compress the receiver. The upper limit is normally determined as the 1 dB compression point, and the lower limit is based on the input sensitivity. So your minimum detectable signal is related to sensitivity, and your maximum will be your 1 dB compression point. Spurious free dynamic range is your second type of dynamic range. SFDR is defined as the 2/3 of the range between the minimum detectable signal and the third order intercept. Regarding this third order intercept and all, we will be studying in our later topics. Okay. So just now, it is a concept in your dynamic range. Just keep it in mind. Okay. So spurious free dynamic range and linear dynamic range are your two types of dynamic range. So we should also know why this dynamic range matters in RF systems. So it determines how well an RF system can handle weak signals in the presence of strong nearby signals. Okay, how well the RF system can handle weak signals in the presence of strong nearby signals. Okay, so there will be some minute signals. Even that signal could be important to some particular system. So even that minimum signal should be handled by the RF system. The RF system should be designed in such a way. Okay, and it's very critical for spectrum analyzers. In spectral analyzers, mostly we'll be using very small signals, which we'll be using in the laboratories, right? So even those signals should be handled by the RF system. Then receivers in crowded RF environments. In crowded RF environments, you'll have both the minute signals and the larger signals. Okay, both should go hand in hand. Then wireless base stations. It's also critical for. So what if your dynamic range is less? Okay, so if your dynamic range is poor, that is, you don't have sufficient dynamic range, what it could cause is desensitization. Okay, desensitization is, that is, the smaller signals will not be taken into consideration. It will be lost. Okay, which could result in deviation in your system. Then blocking of the important signals. Some signals will not even be in the output. Okay, they will be lost. That's called blocking. Then non-linear distortion. Distortion is interference in the signal. So what do we conclude in dynamic range? Higher dynamic range means the RF system can detect very weak signals even when strong signals are present nearby. So it is a crucial for performance in real world RF environments. So that is our dynamic range. So next, let us move on to selectivity. In RF systems, selectivity refers to a receiver's ability, okay, to reject the unwanted signals and to accept the desired signals. Selective, no, you should be selective of what you want. So selectivity refers in RF systems to accept the desired signal and to reject the unwanted signals, okay, that are nearby in frequency. So why does the selectivity matters? Okay, this is very crucial for clear reception in crowded radio frequency environments where multiple signals may be present. Okay, so in real world environments, signals often appear close to each other in frequency. Okay, for example, radio stations, cell towers, there'll be many signals interluding, right? The receiver with poor selectivity, okay, if the selectivity is not sufficient or it's not in the required amount, what happens is it will pick up adjacent channel interference. That adjacent channel interference we'll be seeing the next topic. So what will happen is if selectivity is not proper, okay, so what signal, okay, will pick up adjacent channel interference. So what in the signal which is supposed to go in one particular channel, it will go and mix up with the other channels. Okay, that is called adjacent channel interference, and it will experience distortion. The signal also can experience distortion. The third, if your selectivity is poor, misinterpretation of signals will happen. Okay, the signals could be misinterpreted. Okay, the signal which means one particular thing can be taken for another particular thing. Okay, that is called selectivity. Poor selectivity can lead to the following things: the adjacent channel interference, then experience distortion, and misinterpret signals. Okay, so how can we achieve the selectivity? Okay, the selectivity can be achieved by using band pass filters, okay, intermediate frequency filtering, then digital signal process. So if we use a band pass filter, okay, we'll be studying about band pass filters in our 4th and 5th units. So band pass filters can achieve selectivity in an RF system. Then intermediate frequency filtering can also make us achieve selectivity. Then digital signal processing will help us to avoid the adjacent channel interference. Adjacent channel interference by giving adjacent channel rejection. So that is about selectivity in RF systems. So finally, to conclude, selectivity is all about how well your RF system can focus on the signal you want. How well your RF system can focus on the signal you want and ignore the ones you don't want. Okay, especially those who are the signals such as few kilohertz or megahertz away. So I hope that you are clear with the concepts of selectivity, average value, sensitivity, RMS value, and stress factors. About adjacent channel power leakage. So adjacent channel power leakage is, as I mentioned in the previous topic, a lack of selectivity in your system can lead to adjacent power leakage. So wireless communication and broadcast systems usually assign signals to specific frequency ranges, commonly called channels. So your communication, everything takes place in specific frequency ranges. Okay, like how your RF radio frequency, the range, there is a spectrum, okay, which is 20 kilohertz to 300 megahertz, right? So only between these range should go. So that communication takes place in channels. So channels are often adjacent to other channels of the same service or to other spectrum users. Channels will be each next to each other. Okay. So if the system is designed properly, the consecutive systems, the channels will use only the particular signals. Okay. But if the selectivity or the other parameters are not designed properly in an RF system, this adjacent channel interference can take place. Okay. So in some cases, signal's power may extend beyond the edges of its channel. So instead of going only inside its channel, particular channel, it will go beyond the channel. So this leakage is most often caused by intermodulation distortion. Okay, intermodulation distortion. So if there is distortion present in your signal, it can lead to this adjacent channel leakage. So how is this adjacent channel leakage determined? So we use adjacent channel leakage ratio. So when designing a system itself, we take note of the adjacent channel leakage ratio. So this quantifies the leakage into adjacent spectrum. It's a very important measurement for wideband digitally modulated signals, also called as ACPR or ACP. Spectrum is divided into a transmit and one or more adjacent signals. So what are measured in your ACPR is the power in the transmit channel, power in each adjacent channel. So this ratio is expressed in units of dBc. So how do we measure ACLR? Okay, adjacent channel leakage ratio. How do we measure it? It's measured by using a spectrum or a signal analyzer. Okay, so this measurement requires integration of power over a bandwidth. Okay, so we need to compare the values of power and bandwidth. Therefore, normally it is measured using an automatic measurement function. Automatically, your RF system design will measure the ACLR measurements. And the results can be displayed geographically as well as numerically. This is about your adjacent channel leakage ratio. So with this video, we wind up with the first half of our unit 1, that is the basic parameters of RF system design. Okay. So then the second half we'll be studying about the elements of digital baseband signaling. First, we'll see what is a digital baseband signal, and then we'll study the parameters related to it in our next video. Thank you, students.